All right, you guys get to hear the finale of the Nutcracker Suite as we're going along here. Okay, welcome to the final video of the semester. This is the last video I'm intending to do. However, if you guys want me to put up more, I will do that. But this is the last one that will introduce new things. So, we are now finishing up chapter 30, and what I'd like to do now is in the same way that we defined capacitance and we had those two plates and we said, okay, this is how a parallel plate capacitor, this will be the value, the value of the capacitance. But then we said, okay, well, now that we understand there's this thing called a, can we, let's make an electronic component that is called a capacitor that has those properties. Well, we're doing the same thing with an inductor. So an inductor, which we know of, is we're thinking of as just a solenoid that just goes like that. We are going to now talk about components that are made that act just like that. They may or may not be specifically something like what you're visualizing, but they act just like it. And so they are an inductor. The symbol for an inductor is this, just a little squiggle. And what's the voltage drop across this? So you guys will recall, we have the definition of capacitance gives us the voltage across a capacitor. Ohm's law gives us a voltage drop across a resistor. So what's a voltage drop across the inductor? Well, you already know it. If the inductor has a value of L, then its voltage drop is just minus L di dt. And this is what we define this this property to be, just that. Okay, what if we had a circuit that was like this? What if we had a circuit that had a capacitor C and an inductor L? Well, here's the voltage across an inductor. What's the voltage across a capacitor? You remember we defined the capacitance as C equals Q over V, so therefore the voltage is just Q over C. Equals Q over C. I want to check and make sure you guys can see this green, so apologize me just for a second. It looks reasonably legible. I'm going to go with it. Maybe the blue is better. Okay. Oh, so now the question is, how are we going to analyze a circuit like this? Well, we're going to do the same thing we've done before. There's all sorts of different ways of thinking about it, but why don't we do it with Kirchhoff's loop rule? What does that say? It says that if we start here and we go around this circuit, what's going to be the difference in voltage as we go take a loop around this circuit? Well, the difference is going to be zero, right? The only way there could be a difference there is if there is a source of voltage there. So if we stop at one side, oh, excuse me, I drew that the wrong way. If we stop at one side of a battery, if we just go from here to here, then there'll be a difference. But if we go from here to here, you know that everything has to sum up to zero. It's just a conservation of energy thing. So now we know the voltage of a capacitor, and we know the voltage of an inductor. So we're just going to add those two together. So we know that Q over C minus L di dt equals 0. And okay, so now we look at that and we say, okay, we're done. We have an expression for what happens inside this circuit. But do we? No, we haven't solved anything yet, right? You can't find a solution to that. But then you remember that I is simply defined as dq dt. And so what is di dt is just the second derivative of charge with respect to time. Now I'm going to use my shorthand again, which is, I'm just going to write this as Q double dot. And I'm going to make this very quick because, first of all, you've already seen it before. But secondly, this is also one of those equations where you should be able to just look at it and see what the solution is. So let's go ahead and pull this. Yeah, I'm going to give myself some room here. And yeah, let's just do this. I'm going to rewrite this equation now. And that equation is just, I'm just going to rearrange terms, okay? So I've got Q double dot minus Q over LC equals 0. And remember, this is, okay, I'll leave that up just for a second because you guys can stop this video. I'm going to go ahead and erase it. Okay, just in case you wanted to go revisit this, what I've just done here. What was it? I've confused myself now about what the heck I was in the middle of doing. Oh, just remember that Q is not a number. Q here is a function of time. And so we have this big Q that's a function of time. Well, when we look at a function of time, that second derivative that relates the second derivative with the original function itself. We know we are going to be stuck with something like, or we're going to end up with something that's a sine or cosine or an exponential function. I'm going to go ahead and write as an exponential function here and hope that I have this right. So, believe what we have, e to the minus I. I'm going to call this omega t, and we'll call this Q0. We're going to try that as a function for Q of time. Well, we're going to try that because, like I said, when you see a second derivative, you know that this exponential will return its own value, or excuse me, its own form will return its own form. So what's the first derivative of this? Is we just are going to pull a minus I omega out in front of that. What's the second derivative of that? We're just going to pull another I omega out in front of it. So we have Q0 e to the minus I omega t equals Q of t. What is that? Minus times I times I is minus 1. Minus is plus. So what do we end up with? We have a minus and minus, so that's a plus, but then we have minus 1. So we have minus omega squared Q0 e to the minus I omega t. And what is this? This is just that Q double dot right there. That's all it is. And then we have this equals, let's just do it like this, minus Q, which we've defined right here, which is Q0 e to the minus I omega t over LC, and we know that is equal to 0. Well, we're just going to divide by this. We're just going to divide those terms right out. Let's go ahead and, we'll go ahead. This might have been a plus sign and not a minus, but I'm not going to worry about that a whole lot. Let's cross this out so I can use some room here. So what do we end up with? We have minus omega squared equals 1 over LC. Yeah. So this leads to omega equals square root of 1 over LC. Where I actually am cheating because now I'm saying, let's make this a plus sign instead of a minus sign. Okay, so what does that mean for Q of t? That means Q of t is equal to Q0 e to the I 1 over LC t. Okay, and we're done. What would you do if you wanted to get I of t? You would just take the first time derivative of this. Okay, and that's it. So you guys, actually, I'm just going to remind you, I know we've talked about this in class, and I think we've gone through it in some amount of detail. We can do it more in class if you would like to, but just remember that what these are is oscillatory solutions. So they're cosine-sine solutions. And what does that mean? What it means is the Q goes from 0 to some maximum value, goes back to some maximum value Q0, then goes back down to 0, back to a negative Q0, which means the Q has now flipped on those two plates. Then it goes back to 0 and back to 0. Well, what happens when that's happening on the capacitor? What's happening on the inductor? Well, on the inductor, as Q changes, you have I, the current. And so that current I is running through the inductor as the Q is changing. So when you're up here, you've got an I that is essentially 0. As a matter of fact, it is 0 right at the point where dq dt is 0 at the top and bottom of this cosine curve. And it's maximum as the Q goes through 0. So that's what happens with this circuit. It just oscillates back and forth. The energy will oscillate between being contained within the charge in the capacitor or the current in the inductor. All right, that's it. Congratulations on reaching the final video of this semester.